Did you ever imagine that Rimworld and graph theory have something in common? Rimworld, as described in its Steam page, a sci-fi colony simulator driven by an intelligent AI storyteller. At its core, Rimworld is a storytelling game where the focus is on the colonists and their needs as well as the various threats that the game throws at them. However, the application of graph theory will be focused on the base building aspect of the game. But first, what is graph theory? Graph theory is all about studying graphs. But what are graphs? Graphs are like maps made up of dots as vertices and lines as edges, connecting these dots. And they help us understand how things are connected to each other. Now, how exactly can graph theory be applied in Rimworld? By using graph theory, we can construct a graph of the base and from there, identify crucial buildings and calculate its distance from every other building. First, we need a weighted graph. A weighted graph is a graph whose edges have a numerical value. In this case, those weights will represent cost. Next, we must understand the concept of trees. A tree in graph theory looks like this. Their most recognizable feature is that trees have no cycles. Any path will lead to an endpoint. Before proceeding, let us first apply these concepts to Rimworld. The vertices of the graphs are the buildings of the colony, and the path between them will be the edges. The weights will be the cost calculated using a formula based on the amount of tiles to be traversed.
To get the shortest path, we will use Dijkstra's algorithm. This technique was developed by Edgar Dijkstra in 1956 and is used to find the shortest path between a vertex and all other vertices in the graph. Dijkstra's algorithm works by maintaining a set of vertices whose shortest distance from the source vertex is already known. Initially, the distance to all vertices is set to infinity, except for the source vertex, which is set to 0. At each step, it selects the vertex with the minimum distance from the source that hasn't been processed yet. Then, it updates the distances of its adjacent vertices if a shorter path is found.
For the application of Dijkstra algorithm, first choose a starting point. In our given example, our starting point is storage. Next, label the roads connected to storage with their respective values, and label the unconnected roads as infinity. As you can see, these are the connected values, and these are the infinity that are not connected to the storage. Then after that, find the lowest road value. In our case, it is the workshop. After choosing the lowest value, mark this as permanently visited. Then update the road values connected to the newly visited place by adding the value of the permanent visited place. After that, repeat this process until all places are permanently busy. This concludes by following this process, we can efficiently find the shortest path from one place to every other place.
We now have the distance of the storage room from every other building in numerical terms, for when a building needs repairs or a new one needs to be built. These paths, when converted to a graph, will result in a tree, a shortest path tree to be specific. While Dijkstra's algorithm must be the main focus here, other concepts from graph theory can also be applied. Graph connectivity, for example, refers to how connected a graph is. Vertex connectivity refers to the minimal number of vertices that must be eliminated to make the graph disconnected. Edge connectivity is the same but refers to edges instead. This could be used to identify choke points in the colony. Removal of clutter and better security could then be considered once these are identified.